So in example 1 here, you're being asked to solve the following system of equations using elimination. So let's do one at a time. So we're going to look at the first equation. And what I do is I make a decision about which variable I'm going to eliminate. Now, it doesn't matter which one you choose to eliminate. I could choose to eliminate x's, I could choose to eliminate y's. It really doesn't matter. But in some instances, one's easier than the other. In this case, I'm going to eliminate x because I can easily, multiply the top equation by a constant to get any value, any like constant times x I want, because currently there's a 1 there. Now, what I choose to multiply the top equation by depends upon what I'm going to do with it. What I want to do for x to be eliminated, I want to get the same number in the top equation in front of x as I have in the bottom equation, but I want it to have a different sign. And since the bottom equation has a positive 2x multiplied to the x, I'm going to multiply the top equation by negative 2. That'll put a negative 2 in front of the x, and so eventually when I add the two together, the two equations that is, the x's will get eliminated. I just can't multiply the x part of an equation by negative 2 because that's going to alter the equation. Or to alter the solution of the equation. So what I'm going to do is multiply the entire equation by negative 2. So the top equation is going to become negative 2x plus 4y equaling 6. The bottom equation is left unchanged. The reason why I chose to eliminate the x on this is if I chose to eliminate the y's, I'd have to multiply both equations by a constant and alter both of them. At least this way, I only had to alter one of them. So sometimes that's what helps you make the decision about which is easier than the other. But now when I add the two equations together, the x's get eliminated. Well, that's why I did that. When you get to the stage where you add the two equations together and one of the variables doesn't disappear, then you're not doing it right. And as a side note, don't make them disappear just because that's what you want them to do. You have to make sure they're in a position to disappear. When I add the two equations together, because a lot of students will take the top equation, multiply it by 2, and they say they're going to add them together, and they'll say that 2x plus 2x is 0x, and they cancel. Well, they wouldn't. If you were subtracting the two equations, but that would require you to do some distributive property things. But anyway, if I add the rest of it, I get 7y on the left-hand side equaling 14. I would divide both sides by 7, and y would equal 2. Now that I know what y equals, I can go back to one of the two original equations. It really doesn't matter which one. I can replace the y with a 2. So I did it to the bottom equation. So 2x plus 3 times 2 equals 8, which means 2x plus 6 equals 8, which means that 2x would equal 2. And dividing both sides by 2, I get that x equals 1, which means that the solution is 1, 2. So when you get to a 3 by 3, when I use eliminations, when I have 3 unknown values, or even more, I mean, the more variables and equations I have, the more I have to kind of do this process to eliminate one variable at a time. When I look at these 3 equations, I'm going to choose, to group these equations as so. I'm going to do the first and third equation, I'm going to do the second and third equation. And I'm going to choose to eliminate y. Mostly because I notice that in the third equation, y has a 1 in front of it, a negative 1 technically. Which means I can alter y pretty easily, and that's all I need to do with it. So I chose to eliminate y on both equations. So on the first set, on the third equation, I multiplied it by 3. And that would make the y's disappear when I eventually add them. And I multiplied the third equation by negative 2 for the second set. And what ends up happening when I do that and I add the equations together, I get 14x plus 7z equals 7. And I have negative 5x minus 4z equals 2. So now what I have is I have now 2 equations with only 2 of the variables in it, which gets us back to a circumstance that we had before. Of the two equations I have now, I can either eliminate x or I can eliminate z. It's really up to you. I chose to eliminate z for the sole purpose that the numbers would be a little smaller to deal with than trying to find a common multiple between 14 and 5, which the only one would be multiplying 14 and 5 together, because 5 is a prime number, and 5 is not a factor of 14. So I chose to multiply the top by 4, and I chose to multiply the bottom by 7, because I'm eliminating z, and the z's already have opposite signs, so I don't have to worry about a sign change with this. All I have to worry about is getting the same number in front of the z's with opposite signs. The opposite signs are already there. So if I do that, I get 56x plus 28z equals 28 for the first equation, and I get negative 35x minus 28z equals 14 for the second equation. Now when I add the two equations together, the z's, of course, do cancel. They're eliminated. And I'm left with 21x equaling 42. I divide both sides by 21, and I get that x equals 2. Now that I know that x equals 2, I can go back to one of these two equations that I came up with before and substitute the x value in there to find z. So I chose this one here. I replaced x with 2. 14 times 2 plus 7z is 28 plus 7z. I subtract 28 from both sides and get that 7z equals negative 21. Dividing both sides by 7, I get that z equals negative 3. So now I know x equals 2. I know that z equals negative 3. I can now go back to one of the original three equations here and replace the x with 2 and the z with negative 3 and see what I get. So I chose to take these two and plug it into the very first equation. So the 2 replace the x. The negative 3 replace the z, so I have 2 times 2 plus 3y minus 2 times negative 3 equals 10, which is 4 plus 3y plus 6 equals 10, which means that 3y plus 10 equals 10. 3y would equal 0. Dividing both sides by 3 would give me 0. So my solution would be that x equals 2, y equals 0, and z equals negative 3, which of course I could write the solution as an ordered triple, 2, 0, negative 3.